Hello, I would like to welcome all of you in the International Conference on Signal Processing and Intelligent Computing. Here I am Dr. Zishan Karim, currently serving as an Associate Professor at ComSearch University Islamabad campus. Today I am going to deliver a keynote. The title is Artificial Intelligence to Detect Radio Frequency Signatures of Drones and State of the Art and Research Challenges. First of all, I would like to welcome all of you in this conference. So let's start with the table of contents, the topics that I would like to cover in this presentation. First of all, I would like to cover the drones applications. That is why the drones are too much important nowadays and why they are getting too much popularity. Then we will go towards the drone threats, the threats posed by the drones to the common public and to the national or international institutions. And then I would like to introduce the drone detection schemes, that how we can detect the drones, and then I will further go towards the drone detection systems, that how we can detect and what kind of technologies can be incorporated in this system to detect these drones. For example, I will cover radio frequency based drone detections and vision sensors based drone detections and the sound based drone detection as well. Finally, I would like to conclude my presentation by uh, presenting some future research directions. Okay, let's move toward the drones applications. As you know, nowadays drones have been utilized for transferring goods, medicines, and parcels, and several delivery options. And you can see that drones have services and applications in, for example, in inspection, for example, to take the event photographies and films, and in construction, in agriculture, in infrastructure, in infrastructure mapping, so on. And you can see from this picture the drone is going in to deliver the box to the destination. And for example, the drones can be used to sorry, used to deliver used to thermal sensors for search and rescue operations. And you can see that you nowadays that UAV is equipped with lidar sensor to take the more accurate aerial readings. For example, in creating 3D models that can give you a centimeter level accuracy in detecting features that would be invisible to less sophisticated methods. And you can use for aerial photography, and the drones can be adopted by law enforcement and border control surveillance. And the other thing I would like to mention here is the usage of drones, which is going to increase day by day. For example, in 2013 it was around 12.9, and it goes towards 122, around 122 in 2023. It's in thousand. 2020, the unit here is in thousands. So this is some data which we gathered from one website to present how much the drone popularity is increasing. So nowadays, too many drones people are buying, and because the drone services market is expected to grow from 4.4 billion dollars in 2018 to 63.6 billion dollars by 2025. So it's a huge amount, and there are a number of applications beside that as well. So we can notice that there are too many applications. So that's why the drones are catching the attentions of everyone. Now, as you know that once the drone fly, then it can pose several threats as well. Besides their applications that range from commercial and military applications, it can also pose some serious threats. For example, the rogue drones, which can't be controlled easily, if not monitored or uh, dealt early, then it can pose some serious threats to the power plants, to the president house, and it can carry the explosives, take illegal coverage of homes, and so on. For example, in 2015, one of the DJI quadcopter fell accidentally in the White House, and Once a Japanese protester who was against the use of nuclear power managed to land a drone carrying a container filled with a radioactive sand on the roof of Japanese Prime Minister's office. And so you can see from here, this is the restricted area, and the drone can fly easily inside, and it can pose the several threats to the that institutions to that area. So you can also notice from the data collected the how many times the incident reported. These are the number of times. The total number of incidents reported in 2015 was only 1230, but this number increased to 76% to 2142 in 2019, and it was even increased in 2023. So, but the data here is available till 2019. So, from here, this data, you can notice that how much important is that to detect the drones in the space. So, drone can be a quadcopter, hexacopter, and so on, but the main purpose is to detect them and land them safely to the main area, outside the main area. So, on drone detection systems, let's discuss the drone detection system which exists in the market. First of all, we would like to introduce why artificial intelligence is good for drone detection. The reason behind the AI or artificial intelligence because they are well suited to detect drones due to its ability to process and analyze large volumes of data in real time because the data set you gather about drones in terms of images, in terms of radio frequency signal, in terms of sound, then we need efficient algorithms, and that nowadays AI has a power and to analyze this kind of data quickly. So that's why we need AI for drone detection as well. So AI algorithm can process data from various sensors, for example, from radar, from cameras, acoustic sensors at high speeds, and they can enable rapid detection and response as well. So AI can be integrated from various sensors, as I mentioned, and in result, they can improve the accuracy of drone detection. So drone detection based on their visual characteristics. For example, if you're using the images of drones, then you, for example, the shape, size, and movement patterns, then it can be easily done by using the convolutional neural network (CNN). And the most famous one is the YOLO. You only look once is the object detection algorithm. You can use this algorithm to detect the drones by using the image data set. For example, you can see this is a drone detection system installed on the ground, and here is a drone, and this is the PC which is gathering the radio frequency signals. And for example, this is not sorry, this is not PC. This is the controller which is flying this drone, and passively this data is captured by the drone detection system installed on the ground. So it is a kind of a passive receiver. For example, the USRPs nowadays, Universal Software Defined Radios, so programmable radios. So we use this for drone detection to develop a drone detection system. So this was one figure. The other figure, this model, the big model, is just giving an architecture of you only look once, but the modified architecture. It has the input layer, it has the backbone layer, it has the neck layer, and the head layer. So data from input is injected into the backbone layer, where the pre-processing is done. Mostly the hair in the backbone. You can extract the you just reduce the spatial dimensions, and then in the neck you just try to adjust the anchor sizes, and finally, and in the head usually based on that anchor sizes, the real prediction is done. For example, you can detect the large drone, you can detect the medium size drone, you can detect the small size and extra small size drone based on how you adjusted your anchors and how the more how you adjusted your head and neck, and sorry, the backbone and the neck network. So these adjustments in the existing YOLO systems or the YOLO algorithms, you can easily detect the drone. So this is a kind of AI system which you can use to detect the drone. I have given example of image-based detection. For image-based detection, you can use the YOLOs, and radio-based detection, you can use the USRPs to gather the data and then process it in the future. So we will discuss this detail later on as well. So AI algorithms for drone detection usually use supervised learning algorithms are adopted because of the available data set is labeled. First, we label the data sets. For example, if we take the example of images, so first we label the images and then we process them, that images and images using supervised learning algorithms. And for RF dataset, because the RF dataset is a time series data, so usually recurrent neural networks can assist in analyzing those data. So these are the detection methods: acoustic based. Acoustic means sound. Radio frequency based. Radar based. You may be familiar with the radar. It is a common term. Visual based. Visual means that the camera, we install cameras on the ground and take the images and then process that images. And the sensor fusion. Sensor fusion here means that you get the data from 3 to 4 sensors and then fuse them, and then using that data we can improve the accuracy of the system because we are getting the data from various sensors. Now there is a table which is giving a picture that what is the benefit of those detection methods, like in terms of range, in terms of capabilities, in terms of performance. So let's start with acoustic detection. Acoustic means the sound wave produced by drones motors. Usually, you know that when uh, uh, drones flies, then there is a motor inside. So that motor produces a sound. So we capture that sound and process it. So the range of this detection is only 200 meters and no line of sight required. And the accuracy of this method is very low, and the capability is the detection, identification, localization, and payload detection. So it means that we can, by using acoustic detection, we can have the capability to detect, identify, and localize as well. Whereas the performance deteriorating factor here is the background noise. You know that if drone fly, there is a sound of a drone, but besides there are moving cars, you can hear other sounds, for example, a thunderstorm and so on. So these kinds of noise impact the performance accuracy of acoustic based detection. So afterwards, that's why we are going towards radio frequency detection. In radio frequency detection, you have a radio communication between drone and controller. As I just explained in the previous slide, when there is a drone and it is flying with the radio frequency controller, which we call the remote, so there is a communication ongoing between drone and the controller. So for radio frequency detection, we just gathered these drones radio frequency communication signals, and the range of this is 1 kilometer, and the accuracy is more than the previous method, and it also assists in identification, drone detection, and localization. However, it has a performance deteriorating factor in harsh weather and in the presence of radio frequency interference, and the issue is the kind of autonomous drones. If there is a no communication between drones and the radio controller, the drone is flying autonomously, then we can't detect that drone. So that's why there is a radar based detection. It's Radar is not a kind of passive detection. Radio frequency detection is a passive detection. Radar detection is actually the most expensive solution. However, its accuracy is very high. It works on high frequency waves reflected from the drone. So it is a kind of active device where the transmission and reception both are performed. And its range is very high, it's around 100 kilometers, and line of sight is not required. Accuracy is very high. It also performs the 3 tasks, and the problem here is that usually the usually the you can say that the cross section area of the mini drones or lower side drone is very small. So these kinds of radars usually mistakes them as a stationary objects or birds. So they can't classify easily them as a drone. So this can be a limiting factor. Then came the last one is the visual detection. For this, the cameras are installed on the ground. That should be the very good lens cameras. and the range is usually 100 meters, but it can be extended to 1 kilometer at least, depends on the quality of the camera. So, and then of course the price of the camera will increase. The accuracy is high and it performs also the 3 to 4 tasks, but the problem here is low light condition, dust and fog. But it can be overcome by using the thermal cameras, using the more advanced cameras, so this problem can be overcome. So these were some algorithms or these were some methods which we discussed to detect the drones. Okay, let's move toward the drone detection system using radio frequency signals. So now we would like to focus our attention to the radio frequency based detection system. So how it works and how it can be beneficial and what are the frequencies and what are the existing works in this radio frequency based detection system. So detection system works by gathering various sensors, as I discussed: visual, thermal, radar, radio frequency and acoustic sensors. However, radio frequency signatures of various types of signals using drones typically lies in the range of 2.4 gigahertz to 5 gigahertz to communicate with controllers. So usually our drones are operated in these two frequency range. So drones equipped with Wi-Fi uses 5.4 gigahertz, while the 5G drones operate at 3.5 gigahertz range. Other less common bands are also used, for example 1.2 and 1.3. So radio frequency scanner or sensor can be used to passively listen to the signals transmitted by drone and its controller. For example, this is a drone and this is the radio receiver, right? So this is kind of a passive receiver. This controller is transmitting the data to the controlling this drone. So this signal will also be captured by the radio receiver and then will be processed and uh, for radio frequency detection. Here there are four methods to show the visibility of these methods, how that works. For example, the sound based method, you are gathering the sound from the microphones, and for the images you have installed the cameras and then processing those images. And the final one is the radar. This radar is transmitting and receiving the images, sorry, signals, and through and processing it further for object detection and location estimation. So there can be two methods of radio frequency signal scanning. Radio frequency signal scanning means, for example, you want to gather the radio frequency signal. So there are two methods. The first one is that the receiver listens and decodes the packets being transmitted between drone and its controller. What does it mean by listen and decode? Listen means just gather the signal, right? First one is the listen. And what does it mean by decoded? Decoded means that the message inside that signal will be correctly gathered as well. For example, that message contains drone identity, the drone location, even the speed and the data inside packet. For example, the video streams, what kind of video streams are transmitted between the controller and the drone, that can be detected as well. However, this method requires network sniffing, which is not legal in many countries. So this method is usually not preferred. The reason is that due to some legal objections. So the second method is the RF receiver does not decode the packets. Decode I just explained, drone identity, location, etc. will not be gathered. Only the radio frequency signal that consists of amplitude and phase are detected to find the specific patterns in the captured data. So what does it mean by specific patterns? Let's see the figure on the right. Now you can see that this is the background noise, amplitude and spectrum. So background noise look in this way. So every signal or every radio frequency signal is from either drone or from noise or from other flying objects or any other radio frequency controlled objects. They have a specific pattern. So noise follow this pattern. So this is time domain signal and it's a kind of a amplitude, and this is your frequency signal which is plotted in terms of a spectrogram. So spectrogram of a noise and the signal amplitude is plotted here. So this is for the background noise. Amplitude and spectrogram is plotted. So you can notice that bebop tone. This is a kind of a drone, BPOP, is a type of a drone. It has its own signature. If you compare this signature from the upper one knife, it's totally different, and the spectrogram is also different. And even if you notice from the Mambo drone, it is another type of drone. That this is even a drone, but its signature is different from this one. So, and the spectrogram is different as well. So the second method only focus on capturing the signals and find the specific patterns in the captured data. So specific pattern means the this pattern, like this has its own pattern, the first one is its own pattern, last one is its own pattern. So it provides limited information, and it means that the second pattern even provides the limited information that it detects drone presence, predict drone's make and model, and estimate the drone location. Location means that the direction and the distance from the receiver, how from where the drone signal is coming and how far it is from the receiver. So due to regularity constraint, the second method is mostly used for drone detection. So this method where we just focus on capturing the radio frequency signals, a specific pattern is usually preferred. So you can notice that the signature of background noise drones in terms of amplitude and spectrogram is plotted to show the difference among them, as I already discussed. So, first, you need to know that if you are going to analyze the data, you need to first gather the data set. So, what are the steps to gather the radio frequency data set? This can be shown from this figure. This can be noticed from this figure. For example, this is control and controller, and it's flying this uh, uh, UAV, and video is transmitting, and you can just capture this data. This data actually communication from there. You just capture this one, antenna control, radio frequency capture, broad baseband IQ patterns captures. So after capturing this, you just detect and process. For example, you do filtering, FFTs, and other schemes, machine learning to detect that one. On the right, we want to show that the different signatures of the drones, even the single drone, if you fly in different mode, it has a different signature. For example, mode is on and connected. If your drone is just on and connected to the controller, it has this signal pattern. And if it's hovering, its pattern is a bit different as compared to this one. And if it's flying, its pattern is different. And if it's flying and recording the video as well, then its pattern is different. So it means that from the radio frequency signal, even we can detect the modes of the flying drone, whether it's the only flying, or it's hovering, or it's recording the video as well, or it's just on and connected. So these radio frequency signatures carry a lot of information. This slide actually discusses the existing key radio frequency data sets for research. For example, as you are going to start the research, you need a data set. Uh, Even though you can gather your own data set, but to first get an idea, the existing data sets are very much important. So I summarize some key data sets. For example, this is drone RF data sets, a data set for drones for radio frequency detection, classification, and identification. You can find this from Mendeley website. It is openly available for further research. Cardinal RF dataset, you can find the IEEE data port website. I given the link here, detailed link. NICE drone RF signal classification spectrum dataset, drone radio frequency, remote controller radio frequency signal dataset, drone detect dataset, experimental study of outdoor UV localization and tracking using passive RF sensing. So these are some example of 6 to 7 or around 6 data sets. You can find more as well. There are many available data sets in the literature. So this can be a good starting point if you would like to do research in this area. So these are some state-of-the-art schemes that exist with and without applying AI. For example, this is the paper titled Unauthorized Immature UV Detection Based on Wi-Fi Statistical Fingerprint Analysis. The main idea was just to capture the wireless packet sniffer to capture the transmission of drones. So they use the wireless packet sniffer to capture the transmission of drones. They apply the machine learning algorithm. No, they didn't apply. and they you adopted the feature reduction scheme like extract the statistical feature, and they didn't apply the learning algorithms. The other one that is the micro UV detection and classification paper. They have the main idea was to detect the passive drone and classify using machine learning algorithm. For example, they adopted KNN, K neighbors, neighbors, neighbor, nearest neighbor selection, and the DA discriminant analysis, SVM, and so on. And for reducing the unnecessary features, they use the NCA method, and they didn't apply the deep learning, so on. So, for example, there was one algorithm, 2 to 3 paper I also presented, which focus on the deep learning algorithm. So, here the title was RF-based drone detection and identification using deep learning approaches, and an initiative towards a large open source data drone database. What they did, they conducted a feasibility study on the use of deep learning to detect and identify drones in different flying modes, as I just discussed the different flying modes, and they applied the 3D neural networks to predict and detect the presence of drones, and so on for the other papers. You can just refer these papers. So these are some recent research results. For example, the paper was RF neural net and lightweight deep learning framework for detecting rogue drones from radio frequency signature. What they did here, actually this was our paper, what we did is the radio frequency based detection that can detect the UAVs in complex environment where other detection methods perform poorly. Yeah, so as you know that each drone has a unique RF fingerprint, as we already discussed. The analysis of these RF fingerprint help to detect the drones and its type of and the mode of operation. We proposed the computationally efficient deep learning framework. We named it RF neural net for radio frequency wave detection. So how it was computationally efficient? Uh, in a sense of flops, you can see that we have only 5 million flops and 8K model parameters, and the accuracy was 89% as compared to the DNN, NDCNN, and RF UAV net. So this was our achievement, and this is just to show the different sensors, and we are going to use the uh, RF-based sensors only. This part where we gather the data set from using USRPs. So the other can be a vision based on detection. This I am just putting here to give an idea, although the talk was related to the RF detection, just to give an idea that we can similarly detect the drones using the images or the videos. For example, this was the GANNet Ghost Auto Anchor Network for detecting various size drones in the earth. This was our paper, and it's published in IEEE VTC 2023. What we did, we performed a multi-class and multi-target drone detections, and in the challenging weather condition and even in the night. So this paper was more focused towards detecting the data in the night, drone in the night, sorry. So we have IR data sets, night vision data sets, and we have achieved this for a very small or tiny object. So we introduced the extra small anchor P2 in this model's head. So in this part of this, we introduce the extra small X small model to anchor to just focus on very small uh, thermal drone in the thermal images. Usually in thermal images or data set, we have a very small drones. So we gathered around 5105 IR images. So these were our results. For example, this you can see that it's very hard to see from the naked eye, but it's clearly our algorithm clearly discriminates between birds, drone, helicopter, and plane. We have four types, different types of classes here, and we achieve overall 96.2% precision, and as compared to the YOLO V5, which has 94.8%. And we have for helicopter 99% precision. Is almost similar to the GhostNet YOLO V5 we compared with this one. So for drones, we have around 90% precision. So this was a good research and very much impactful. So we already provided these source codes as an open source, and you can find from internet. So this was another paper which also relates to the images translearn ULOX. Here we try to detect the multi-class and multi-scale UAV identification. And here we just trained the YOLO V5 and V7 model on the pre-trained weights of the COCO data set. So that's why we call, due to implementing the transfer learning, we call it as a translearn YOLO V7. So these results, you can see that our results was much improved as compared to the existing schemes. Similarly, you can go for a sound-based detection. I think time is running out. So in sound, you just capture the data set in terms of sounds and just process using machine learning algorithms. For example, you can use the LPCC and MFCC to extract the important feature, and after extracting the features, you can go for SVM for classification for a simple machine learning algorithm. So this was our paper published in IEEE. And so these are some results. These are spectrograms, and you can see that SVM classification results with MFCC using different color functions. So we have applied linear, cubic, and quadratic, and so on color to improve our accuracy and sensitivity and specificity. So in future research direction, if you want to to do research, you can research and designing the efficient algorithm to clean the raw data from the open source data set, and you can work on capturing the radio frequency signals in real time using advanced software defined radios. You can work on the SNR improvement and detection of signals in RF signals in low SNR range. Low SNR means that when the SNR is very low, so the detection accuracy or the classification accuracy should be improved. That can be a target. Regarding images, you can work on the integration of vision transformer and attention modules to enhance the required features of the drone image data set. And thank you for listening. And if you have any question, I will be happy to answer. Thank you very much.